actually did section 34, most of it during J-term. So it started off with estimating things using sigma notation, which you guys did in Algebra 2. So as a quick review of that, if you have something like I equals 0 to 5 and you have 2i plus 1, you start by plugging in I equals 0, then you plug in 1, 2, 3, 4, and you stop at 5, right? So you find all those values, you add them together, and you get your result. Do we feel comfortable with that kind of stuff? Okay, so then we talked about Gauss, who was a child prodigy, and he added up the numbers 1 through 100. So he came up with summation formulas later in life. He was a brilliant mathematician. And then I told you that Riemann studied under him. So Gauss came up with these summation formulas, which basically says if you have a number, so let's say you have 5, and you added 5 to itself n times, this is what it would look like, 5 plus 5 plus 5, right? And this would be a total of n times. What would you get? What number would you get, though? No, it's n times, guys, not 10 times. 5n, exactly. N is a number, guys. All right, so you would get 5n. So that first summation formula, I think, is easy enough that you guys can know that one. I'm not going to give that one to you. And then the second one is, so the one over here, is his Gauss formula. So he added up the numbers 1 through 100. 99, 100. And if you remember what he did is he paired the numbers, the first and the last numbers together, and he said, okay, those add up to be 101. 1 plus 100 is 101. But 2 plus 99 is also 101. 3 plus 98 is 101. And he said, okay, if I have 100 numbers, how many pairs do I have? 50, right? 100 divided by 2. And then he added the first number plus the last number. Okay, that's here. N over 2 is the number of pairs. First plus last is n plus 1, right? 1 plus n. Okay, that's the Gauss formula. I will still give that one to you, although I think you should know it because we did it in Algebra 2 even. All right, the second two, I don't expect for you to know. It's fine if you don't know these. I will give these to you. So let's work this out. So let's do it with an infinite number. So we're going to skip to this one. So do you see where it says find the infinite sum of the limit as n goes to infinity, I equals 1 to n? Okay, this is a tough one to start out with, but I'm assuming that you have some basic knowledge about sigma notation, which you guys did during J-term. We'll see. All right, so basically with sigmas, we can kind of distribute a sigma n. Like when you have things like, you don't have to write this, but if I had 1 plus 2i, and I started at I equals 0 to, well, we'll start with 1. I equals 1 to 5, let's say. You could write that out and do 1 plus 2 times 1, plus 1 plus 2 times 2, plus 1 plus 2 times 3. Do you see how that works? Or you could break it apart and add up all the 1's together and add up all the 2 times numbers together, and you can actually pull out that 2. Do you guys see what I'm doing here when I say this? Could we group all the 1's together and say, oh, I have all the 1's first, and then group all the 2 times something, 2 times something, 2 times something, and then pull out the 2? So we had 1 a certain number of times, then we had 2 times 1, 2 times 2. So couldn't we pull out the 2 with the opposite of distributive property from all of them, and then 2 times 1, 2 times 2. That's what we're going to do. So we're going to use these skills with our summation. Okay, it's going to be really weird at first. Are we ready? This is rough to have on a Monday morning. I'm sorry. I apologize. All right, so what we're going to do is we're going to FOIL this out. So I'm going to take my 1 plus 2i over n multiplied by 1 plus 2i over n, and we're going to FOIL it. So when I do, I'm going to have 1 plus 1 times 2i over n is going to be 2i over n, and then the inner is also 2i over n. So what am I going to get? 2 of the 2i over n's. In other words, 4i over n plus, and when I FOIL the last part, when I multiply the 2i over n multiplied by itself, I get 4i squared over n squared. Okay, we can leave off the limit for now. So I'm going to have 1 plus 4i over n plus 4i squared over n squared, and I'm multiplying by 2 over n. We are. We're going to throw that in as well. So we're going to have 2 over n plus 8i over n squared plus 8i squared over n cubed. I haven't related this to area or anything weird yet, but it's going to be related to what we're going to do with area. Okay, so now what do you think we do? What do you mean we add them up? So what do we do? What was I talking about with the sigma? What can I do with this sigma? I can kind of distribute it and I can rearrange my terms, right? So I can put all of my 2 over n's together, and then all of my 8i over n squareds together, and all of my 8i squared over n cubes together. So here's what it's going to look like. It's going to look like I equals 1 to n, 2 over n, plus I equals 1 to n, 8i over n squared, plus I equals 1 to n, 8i squared over n cubed. And then always think about what you have on these. Okay, what is this saying? The first part, that 2 over n, is saying that you have 2 over n added to 2 over n, added to 2 over n, added to 2 over n, right, n times. That's what that's saying. This is just a constant. That is the same for every single term. Why is that the same, even though I have this sigma thing going on? Because usually with sigma, you plug in like things. You're like, oh, I'm going to plug in 1, then I'm going to plug in 2, then I'm going to plug in 3. Why am I not doing that here? I can pull it out, but like what's happening? Look at these ones. Would I plug in a 1, a 2, a 3 here? There's no I. Exactly. If there's no I, we kind of just pull it out front. And what does that leave in here? It leaves a 1. Okay. So the rule is going to be anytime something doesn't have an I with it, we can pull that out. So like this next one would be 8 times 1 over n squared plus 8 times 2 over n squared plus 8 times 3 over n squared. And think about like the distributive property. What could I pull out to the front? I could pull out an 8, but I could also pull out a n squared, and then I would have 1 plus 2 plus 3, right? Does that make sense? That's what we're doing here. So I'm pulling out anything that doesn't have an I. 8 over n squared, I equals 1 to n, and Ari says I'm left with an I. Does that make sense? Because that would be, when I replace I with 1, 2, 3, it would be 1 plus 2 plus 3 plus 4 plus 5. You get it? All right, so what do we think we do on the next one? I pull out a 8 over n cubed, and I'm left with the summation of I equals 1 to n of I squared. So here's where Gauss helps us out because he came up with these formulas. So he said if you have 1 times 1 times 1 times 1 times 1, or not times, 1 plus 1 plus 1 plus 1 plus 1, n times, what do we get? N, right? If I add 1 to itself n times, I get n. So this first part is 2 over n multiplied by n. How about the next part? If I add up 1 plus 2 plus 3 plus 4 plus 5 all the way to n. Nope. That would be if I multiply. So 1 plus 2, this is the Gauss formula. This is what he came up with when he was like, I hear he was younger than 10 years old. I don't know how old he was.
Times n plus 1 over 2.
It's number of pairs. So n times n plus 1 all over 2. Okay, and you can get that. I'll give you the formula. It's right here, so you can have that formula. All right, so if I add up I squared, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way to n. That's the other formula. So that other formula on that page was this one right here. So the n times n plus 1 times 2n plus 1 all over 6. And after you do your homework, you'll have it memorized anyway. So I'll give it to you, but you'll memorize it. Okay, now we're just going to simplify. So if you remember, these were as the limit as n went to infinity. Okay, so we can do that. We can find the limit as n goes to infinity of all of this. Okay, and it's not as bad as you think. We can do this. So now it's just an algebra problem. So you guys were telling me, oh, that's just going to be 2 there, right? So we have 2 plus, and we start reducing things out. So my n squared and n make an n, right? I multiply my 8, or my 8 and my 2 actually could reduce out to 4. So I have 4 n plus 4 all over n. You see that? So I distributed my 4n plus 4. I can start reducing out the other stuff. So my 8 and my 6 reduce out to 4 and 3. One of my n's reduces out, so I have an n squared on the bottom. But I got to FOIL out that top. So I'm going to have 4, and then as I start FOILing, I get 2n squared plus 3n plus 1 all over 3n squared. And again, I'm taking the limit as n goes to infinity. So I'll eventually show you a trick where you can get the answer right now, but let's continue FOILing. Think about how I could get the answer right now. Think about as n goes to infinity, what terms are going to matter. So here's what's happening. So I'm going to get my 4n over n, right? This n's going to go in here and here. So I'm going to have 4 plus 4 over n. I distribute in here, so I'm going to have 8n squared over 3n squared plus 12n over 3n squared plus 4 over 3n squared. So in other words, I have 2 plus 4 plus 4 over n plus 8 over 3 plus 4 over n plus 4 over 3n squared. So what terms matter as I take the limit as n goes to infinity? You know what I mean by that? Yeah, the 2, 4, and the 8 thirds. And anything that has that denominator where it's like heavier on the bottom, right? If you have 4 over infinity, it goes to 0, exactly. So these 3 terms go to 0. So now think about how you could get that from here, because that's going to save you some work. And when I first taught calculus, I made my students multiply it out every single time. And then finally I was like, why am I putting them through this pain? Like really, like think about what your largest degrees are. Okay, so if I have 4 times 2n squared over 3n squared, those are the only things that have an n squared. Those n squareds are going to cancel. I'm going to be left with 8 over 3. Do you see it? Do you see how these other terms don't matter? They're insignificant? Because I'm dividing by something that has n squared, and these had a lesser degree. Does that make sense? So we'll use that on the next step. So we end up getting 2 plus 4 plus 8 thirds. So if I put them all over 3, so 6 plus 12 plus 8 over 3. 26 thirds. So that's my answer. Look at 3. Looks kind of like an 8. 26 thirds. Okay, so that was an area that we just found, but I didn't really tell you what we were finding the area of. So now let's try an area one. Okay, so let's revisit the example. Y equals x squared. So I have a parabola, right? And I'm finding the area between 0 and 2. So I want to find this area. And what we're going to do is we're going to use an infinite number of rectangles. So we have all these right-hand rectangles. And if we take an infinite number of them, we're not going to have any of those little triangular parts that are above the curve, because an infinite number is going to fill that perfectly so that it's like this. So we're going to have this area right here. Right? Does that make sense? Do you guys get it? So if I have an interval from 0 to 2, and I divide it into n subintervals, what's the width of each one? We just talked about this. Nope. No. Oh, guys. If I divided it into 100 subintervals, it would be, what was the original width? 2 divided by 100, so it would be 2 over 100. Do you guys remember doing that example?
2 over.
So what is this going to be? It's going to be 2 over n. So we often write this as delta x, so this is going to be 2 over n. So it depends on how wide it was originally. If I went from 0 to 3, it'd be 3 over n. If I went from negative 2 to 2, what would I put? 4 over n, because it'd be a width of 4 divided into n pieces. So in order to do this, we use the equation delta x is equal to b minus a over n. So in this case, we had b was 2 and a was 0. So 2 minus 0 divided by n. You guys can do that without memorizing that formula. All right, so if we want to use right endpoints, we have each one is 2 over n. So this was one of the 2 over n's. This is another 2 over n. This is another 2 over n, another 2 over n. And if I want the ith rectangle, and I want the right-hand side of it, what x value do I use here? Yeah, I want that 2 over n I times to get to the ith rectangle, right? So you can put 2 over n multiplied by I or 2I over n. But if we want the left one, that ith rectangle, geez, just like we talked about, like if I was trying to get the third rectangle, I would use the one over here on the left side, right? That would only be 2 of these 2 over n's. That's not what, I mean, that's is what we want, but it's a little bit hard, right? Because if I want the left-hand endpoint, this is going to be 2 over n multiplied by I minus 1. Okay. Think about the process that we just did with sigma. Do we want to do more distributing than we need to do? No, it's a complicated process when we're calculating this with sigma. So we want the most precise, like tiniest term possible. So we want the 2I over n. That's why we're going to use right-hand endpoints for these. I mean, choose your battles. If you guys want to go with left, I will grade it with left-hand endpoints, but I'm telling you the easier one is right endpoints. So you might see your book have this notation. I will never use this notation because for you guys to memorize a notation that doesn't make any sense for you, we're not memorizing things that don't make any sense. We're thinking about what we're doing for these for this area. So what am I doing? I'm finding the area of each rectangle, right? And then I'm going to add them all together, even though there's an infinite amount. That's okay. So I find the area of a rectangle by multiplying the width times the height, right? When you see this f of m sub I or lowercase m sub I or whatever it is, this is the height, in this case, of the ith rectangle, because there's an I there. And this delta x, well, that's the width of each rectangle. So what are we doing? We're multiplying the height times the width. And we're doing it for the first rectangle, plugging in I equals 1, the second rectangle, the third rectangle, all the way to the nth rectangle. Okay? So like I said, you don't need to write that notation. You could just say something like sigma height times width. So we want the height and the width. Well, what's the width? 2 over n. Be careful. People that don't understand this process and eventually take a quiz on this, not totally understanding it, will put 2I over n. That's the biggest mistake I see calculus students doing. 2I over n is not the width of the interval, right? That's the x value for the right endpoint. Okay, that's not the width. All right, so what's our height? So if we were doing this with our normal left-hand sum, 0 to 2, and I said to divide it into 4 subintervals, let's say. You don't have to draw this. You would have 0 0.5, 1, 1.5, and I asked you for the height at 0 0.5. What am I plugging it into? I'm plugging it into x squared, right? I'm plugging it into the function. So my height is going to be whatever function I have multiplied by the right-hand endpoint. The right-hand endpoint's the thing with I, 2I over n. You can use, I'll say right, yeah. And remember, we're going to test on this, so we're going to learn it, we're going to test on it, and be done with it forever. Isn't that exciting? Okay. So our function was x squared, right? So I take that right-hand endpoint and I replace my x with it. It's 2I over n. That x value is now squared. Okay, now we're ready to go. So we got it. Start to simplify. So try it along with me. Be active note takers, right? So as I square that out, I get 4I squared over n squared multiplied by 2 over n. So I get the summation of I equals 1 to n of 8I squared over n cubed. What can we pull out? 8 over n cubed. Anything that doesn't have an I, we can pull to the front. So I'm going to pull out that 8 over n cubed, and I'm going to be left with I equals 1 to n of I squared. Our friend Gauss gave us this. And that's how we're going to do integrals too. We'll say like 1 to 5, right? Because it's saying the interval, saying from this to this, right? For the integral, it's the interval that we're talking about. Okay, so if I have 8 over n cubed, and I'm going to multiply by the summation of I squared right here. So it's going to be n times n plus 1 times 2n plus 1 all over 6. And this is what I'm going to take my limit as n goes to infinity. So I'm okay if you don't write it till the very end. But really, it's been here. It was here all along, right? L squiggle. Did I tell you guys that? I told my calculus class one time they could just write L squiggle and I'd know what that means. And I said, I mean, obviously don't write that on the AP test. And then after the AP test, I had a student that was like, oh, I just wrote L squiggle. I'm like, no. Like, I let you do shortcuts, and then you still do it. Yeah, kind of. It's kind of annoying. All right. So here we go. So we're going to FOIL it out. And we're going to reduce out that like the n and the n cubed can be n squared, and the 8 and the 6 can be 3 and 4. We'll do this a lot. Okay. So I'm going to have 4 over n squared multiplied by 2n squared plus 3n plus 1 all over 3. Do you guys see the terms that will matter? Think about it. So you can distribute that 4n if you want. It's not a hard one to do. So we get 8n squared plus 12n plus 4 over 3n squared. And then you would bring that 3n squared into each piece, but what's the part that matters? This part right here. The rest of them are going to be like over n or over n squared. So what's my answer? 8 over 3, that's the answer. So that is the area under the curve y equals x squared from 0 to 2. Okay, let's try another one. Any questions on that so far? I know it's annoying. Left-hand endpoints. So we'll do it. It's not that bad for this one. I mean, when the function's something easy like just x squared, it's not bad. But when you have like x squared minus 5x plus 2, like it can be really annoying. Okay, so our function was x squared, right? So think about what function or what x value we're plugging in. So we said for a left-hand endpoint, we would plug in an x value of 2 over n multiplied by I minus 1. So we're going to have 2 over n multiplied by I minus 1. Squared. So it's x squared, right? Times delta x, what's our width of each rectangle? 2 over n. Exactly. Nope, not 2I over n. Don't confuse people, Ari. It's just messing with you guys, but now everybody's going to think 2I over n. All right, so we're going to square it out. So I'm going to have I equals 1 to n. So I'm going to have my 2 over n, well, it's going to be squared, right? So I'm going to write 4 over n squared multiplied by, if I FOIL that out, I squared minus 2I plus 1 times 2 over n. Lovely. Yeah. It's not an x value of 0. It's saying like the first rectangle, the second rectangle, the third rectangle. So it'd be 1. So she was asking at the bottom, should it be I equals 0? She's thinking like the x value is equal to 0. Like we're going 0 to 2. But it's not actually. It's saying like the first rectangle, the second rectangle, the third rectangle. All right, so we're going to pull out 8 over n cubed. And then we're going to have a big sigma. We're going to have the sigma of I squared minus 2I plus 1, so I'm going to break it apart into 3 sigmas. So I'm going to pull out that negative 2, oops, not negative 2I, so negative 2, and then I'm going to have sigma of I, and then I'm going to have sigma of 1. If you want to be lazy and not do I equals 1 to n every single time, I don't care. to have our 8 over n cubed, and we're going to multiply by summation of I squared. So that's going to be n times n plus 1 times 2n plus 1 all over 6 minus 2 times summation of I n times n plus 1 all over 2. And summation of 1, if I have 1 plus 1 plus 1 plus 1 plus 1, what do I get? N, right? Because it's going to be 1 added to itself n times. A lot more complicated, isn't it? A little more complicated. All right, so our denominator involves an n cubed. The only term we need is the one that involves an n cubed. Let's use the shortcut on this one. Do you see how we have an n multiplied by a 2n squared? Do you guys see that? So all I'm going to have left is going to be like an 8, well, actually 16. Do you guys see why it's 16? Because the 2. So 16n cubed over 6n cubed. Okay, again, I have n cubed. So if I have n cubed on the next term, is any of the next term going to matter? No, because the highest degree I have is n squared. What about the last part? No, it doesn't matter. All of these will go away because they're divided by that n cubed. So I get 16 over 6, which is 8/3, because I take the limit as n goes to infinity, right? So all those other terms, when I take the limit, they all go to 0. So I'm left with 8/3. They were the same answers, and they should be the same answers, right? It's still representing the area under the curve from 0 to 2. All right, so that's what this is saying. So it says the area under the curve is just the height times the width, height times the width, height times the width for each of those rectangles. That's what this is, height times width for n rectangles. So we write it like this. You do not need to write it like this ever. I'm fine if you just know where the formula, or like know what your right-hand endpoint is and plug it into the function. Okay? All right, so let's do this next one. So find a formula for the sum of n terms for the function. Find the limit as n goes to infinity. Man, I should have done something more interesting than 0 to 2. Now you guys are going to think everything's on 0 to 2. If it was on 0 to 3, what would our width be? It'd be 3 over n, right? So we're on 0 to 2 again. So the width, delta x, is going to be 2 minus 0 over n, which is 2 over n. And if I want to talk about the ith rectangle, its x value is going to be 2I over n. So delta x is the width. So if we put it together, we have the height times the width, 2 over n. What's our height going to be? Two times 2I over n minus 2I over n squared. Oh, I ran out of room. Do you guys see where that comes from? We have our function, and we're plugging in our x value into the function. So saying a generic ith rectangle, that would be for I equals 1, the first rectangle, I equals 2, the second rectangle, I equals 3, the third rectangle. Because we're using this function here. So we're replacing the x's with 2I over n. You see it? So just like when we did like breaking it into 100 rectangles, if I had this was the first one, second one, third one, right? 6 over. Hang on, say it again. What? Yeah, like we had an f before. We're just plugging it into the function. Yeah. So like it was just like what we did when we did like 100 rectangles, well, not 7 rectangles, but n rectangles, right? So you could do any number. All right, so we're going to simplify. So we go I equals 1 to n, and of course we'd have our limit, which if you don't write that, that's fine. So I'm going to do the limit as n goes to infinity, and I start to simplify. So I'm going to have I equals 1 to n, 4I over n, minus 4I squared over n squared, all multiplied by 2 over n. See how I got that? Just algebra. And I'm going to multiply the 2 over n. It's confusing, in. So I equals 1 to n, and I'm going to have 8I over n squared minus 8I squared over n cubed. And then I'm going to break apart my sigma. So I'm going to have the first sigma. What am I going to be able to pull out of the first sigma? What can I pull out of this? Yeah, the 8 over n squared. And I'm left with the summation of I. And then the second one I can pull out the 8 over n cubed, and I'm left with the summation of I squared. So I have my 8 over n squared, summation of I, that's going to be the n times n plus 1, all over 2. The summation of I squared is the n times n plus 1 times 2n plus 1, all over 6. Okay, see how smart you are. Negative 8 over 3? I don't know, maybe. I feel like it should be positive. I think it's above the axis. I think it's the downwards parabola that has an x-intercept of 0 and an x-intercept of 2. So I think it should be positive. All right, so our largest degree down here was n squared. Do I have an n squared on top? Yeah, I have 8n squared over 2n squared. The rest of them are not n squared on the top, right? Minus, the biggest one here is n squared. Ooh, should it be n cubed? Yeah. I just couldn't read my own handwriting. Yeah, n cubed. The reason I knew is because that would go to infinity, and it's not an infinite area. So that should be an n cubed there. So I could have gotten a bonus point. So I have 6n cubed all over. What will it be when I multiply out the top? What's the highest degree? N cubed, and it's going to be 16, right? So I'm going to have minus 16n cubed all over 6n cubed. So as I take my limit as n goes to infinity, I end up getting 8 over 2 minus 16 over 6, which is 4 minus 8 thirds. So 12 thirds minus 8 thirds. So the answer is 4 over 3, yes. Okay, does that make sense? All right, let me show you your homework.